Okay, let us continue with the second part of our seminar. So now Professor Felipe Wallison will introduce Professor María Ángeles Rodríguez Bellido. So Felipe, please.
Okay, thank you very much, Diego. Good afternoon to everybody. It's my pleasure to introduce Professor María Ángeles Rodríguez Bellido de la Universidad de Sevilla. Okay, Professor María Ángeles es profesora titular de la Universidad de Sevilla, and she's an specialist in chemotaxis systems and fluid mechanics. So she has been working on this for a couple of years now. So it's a pleasure, Professor María Ángeles, to have you here and meet you in person. I have heard your name, but it's nice to put a face on someone's name. And it's a very interesting talk on optimal control problems for chemotaxis models. And please, Professor, thank you very much, and feel free to start whenever you want.
So thank you very much for the presentation and also for the invitation to participate in this seminar. To the organizers, it is always a pleasure to be here. So I will talk about this subject that has been made in collaboration with many researchers, some of them known by you, for example, Francisco Guillén González from the University of Seville, also Diego Rueda and Elder Villamizar from the Universidad Industrial de Santander in Colombia, Ezequiel Mallea, that now is in Universidad Católica del Norte in Chile, and Pablo Braz and Silón Perosato from Universidade Federal de Pernambuco in Brazil. So, so the talk is organized. First of all, I would like to introduce the chemotaxis PD model that we're going to treat, because it is necessary to know what are the difficulties and what are the motivations in order to introduce an optimal control inside the system. And at the end, I will present some conclusions and references in order to read about and to know more about this subject. And for those that don't know what chemotaxis is a biological process of movement of living organism towards or escaping from a chemical substance. So you can see these pictures. This is the attractive situation, and this is the repulsive one. And also there is an interaction, and in some sense, the living organism make increase the quantity of chemical substance or decrease this quantity. So what we are going to take into account? First of all, we are treating with biological variables. So it is very important to recover at least the positivity of the unknowns. We are dealing with two kinds of variable. One will be called U. U represents normally a cell density or a living variable. And V normally will represent an stimulus. It can be, for example, like here, a chemical signal, nutrients, oxygen, vasculature, or even it could be a light, or even a magnetic field, something that enters into the system and interacts with the biological variable. And we treat at like a macro scale continuous medium. So we use a PD system in order to model this biological behavior. The most known, or the big group of systems that model chemotaxis are represented by two equations. The first one is the equation for the living organism, that at the beginning is a parabolic equation, but the problem is that what is called a chemotaxis term is introduced, and this term breaks, in some sense, the parabolic behavior of the equation. This chemotaxis term is just that represents if the living organism is moving toward the high concentration of the chemical substance or escaping from. Attract or escape depends on this kappa constant, that in the case of kappa is positive, that means that the living organism moves toward the chemical substance. And if kappa is negative, that means that a living organism escape from the chemical substance. And sometimes there is a source term that can model, for example, the increasing or decreasing behavior of the living organism. The second equation, the equation for the chemical substance, generally is more regular. And if you see this structure, it's a parabolic equation, classical, even with a drag term that is more or less easy to treat in order to obtain regularity and existence for the system. And living organism enter into the equation for the chemical substance here. In this case, if the term is positive, that means that if the living organism increase, it provokes also an increasing behavior of V. And if the source is negative, it could decrease in some sense also the quantity of V. In the literature, we can find parabolic systems, or sometimes it is also treated the case where beta, this constant beta that appears in the equation of V, is 0. In this case, instead of having a parabolic equation, we have an elliptic one. And in some sense, it's easier to treat in order to obtain existence and regularity results. Also, sometimes you could find also that this gamma constant appearing in front of the Laplacian is 0. And in this case, we do not have a PDE equation for V, but an ODE. So it is also possible to find this in the literature. And well, the logistic term could appear or not, depending on the sign, depending on if alpha is 0 or not. So we are dealing with this kind of systems that were introduced by Keller and Segel in the 70s, and that has the behavior that I explained just before for U and V, complemented with normally a homogeneous Neumann boundary condition for both unknowns, for the living organism and the chemical substance, and also with initial condition that must be considered positive if we want to recover the positivity for U and V for the whole time. So this is very important. And well, the rest of effects has been treated in the previous slide. The mathematical skills necessary in order to treat with this kind of equations are the following. Of course, as parabolic equations, parabolic diffusion reaction equations, all the tools involved in the analysis, estimates in weak space, in strong space, conservation of some quantities, and also tools in order to preserve the positivity of the unknowns. It is very, very desirable if we have something like an energy equality or inequality associated to the system. Because if we have that, the inequality in the sense that we have the derivative in time of energy, and here a dissipation, if we have that, we can recover, for example, estimates for large times. And it is also possible to find estimates in order to have existence and regularity results. In the literature, there are lots of works that are proved by using semigroup theory with heat Neumann kernel. So this is one very extended method of proof for this kind of systems. And we have to remark that normally the regularity for the chemical substance is higher than the regularity for U. So in order to have this energy equality or inequality, it is necessary to work carefully with the adequate test functions in order to obtain this kind of estimates. For those that don't know nothing or so few about chemotaxis, there is a very interesting and big work by Belomo, Beloquitao, and Winkler, published in 2015 that recover a big amount of systems, and the main results of a system's asymptotic behavior, regularity associated to this problem. In general, we have taken this one that this has a form very similar to that one that I have presented. And in this case, they say that if we have that the source term F and G has this kind of regularity, C1, they are positive when U is 0 or V is 0. And the initial conditions are regularity enough, it is possible to prove the existence of a classical solution, classical in the sense that continuity in time and space, and C21 in time and space, but for a finite Tmax in principle. But they also said that if Tmax is finite, that means that this norm, the L infinity norm for U and the W1Q norm for V, explodes when T approaches Tmax. That means that if this norm is bounded, therefore Tmax must be infinity. And in this case, we have a global in time solution for the system, but it is not so easy to prove. But this is a very interesting result that appears in this article. The tools involved in order to prove the result consider Banach fixed points, semigroup theory, and Galliardo-Nirenberg inequalities. But not all the kinds of chemotaxis model that we want to analyze can enter into this general rhythm of the system. For example, if we wanted to introduce a control, we introduce something that depends on F, and all the results, all the hypotheses involved in the previous results does not contain this possibility. So previous result, it's not possible to be used in order to prove results associated to a control. So it must be modified in some sense. As I said before, if we are able to prove the boundedness of the L infinity norm for U and the LQ norm for the gradient of V, in this case, we know that the solution obtained is not local in time, but global in time. And in this article, there are extensibility criteria presented for the 2D domains and the 3D domains. But as I said before, it's not so easy to satisfy in most of the cases. In order to center a little bit what we did, we started by analyzing this case, this simple case, simple because we consider a repulsive chemotaxis system, and we consider that the source term is 0, and the equation for the chemical substance has this source term, this production term. So we started by analyze first the system of solution for this system, and after that we analyze what was the effect of introducing the control in this equation. So we consider U to the power P for P equal 1, P between 1 and 2, but it is an open problem to consider P greater than T, and we will see in a minute. As I said before, it is important to recover positivity, and we are able to prove that the solution for this system is positive for both unknowns. To have the conservation of U that can be deduced from the boundary conditions and the equation for U, if we integrate this equation in space. And it is also a key point to obtain an energy equality. In order to have this energy equality, equation for U must be tested by an adequate function and the equation for V for another one. So depending on the value of P, we can consider log U as test function for U, or the power p minus 1 if p is different from 1. And always we take this test function for the equation for b. And in this case, we are able to obtain this energy inequality that make easy the obtention of estimates. And with this estimate, we can apply fixed point theorems in order to have existence of solution for this problem. But normally, from this energy inequality or equality, we can deduce the same regularity, this that we call weak, L infinity in time, L2 in space, or L2 in time, H1 in space, for gradient of P, and for, not for U, but for U to the power P over 2. So here we can see that the both unknowns has different regularity, and the regularity for B is 1 degree higher in space than the regularity for U. But it is not possible to obtain directly the regularity for U. We only obtain for a power of U, for the power P over 2. And this makes difficult to recover the regularity for the gradient of U, because we have something like that, like this expression that appears at the bottom. So in order to have regularity for gradient of V, we use this written. And here it is necessary to have that this term, this power of U, is not singular. So if P is smaller than 2, it is possible to treat the regularity for gradient of U by taking the regularity for this both term, the power of U and this gradient. But if P is bigger than 2, this term is singular, as it is not possible to recover regularity for gradient of U. So this is the reason why we only reduce our study to values of P between 1 and 2. And it is also possible to obtain some estimates for U also for the integral in omega. The results obtained for this system are, for P equal 1, the results were proved by Chislab and collaborators in 2008. For P equal 2 was obtained in collaboration with Guillén González and Rueda Gómez. And for P between 1 and 2, also with the same authors. But this, in this case, we obtain existence of a strong solution only for 1D domains and 2D domains, not for 3D. For 3D, it was not possible. And in the case of existence of weak solution, it is global in time, and it is possible with some restriction, but it is possible to obtain convergence to constant states in most of the cases. As usual in this kind of system, results in 2D, for example, existence of blow up on global regularity, are normally open problems and depend on the data. If we treat the case of attraction, we will analyze only the case when the source term for V is a power is U to the power 1. So in this case, it is possible to rewrite the system in this form. It's possible to prove positivity. It is possible to prove also conservation of the total mass of U and boundedness for the total mass of V. But the existence of energy estimates, it is only proof in 1D, because the problem is that the dissipation that we obtain, it is okay, but the energy that appear here has a term that is not good, and it is difficult to bound. And in fact, it is only possible to be bound when we treat 1D domains. So this is also something difficult to treat. There's a lot of research in this sense for the attractive system. Many works in the last 10 years by Nagai, Velázquez, Winkler, Tao, Belomo. Normally, there is no blow up in 1D. And in 2, 2D and 3D cases, normally the systems of blow up or not depend on this quantity, if it is big or not, or is bounded by some limit. And normally, as I said before, a blow up is expected in these cases. In the 2D case, the attractive system has been studied mainly by Winkler, also by Lancade, with and without logistic reactions. And there's some references here that you can consult. And the 3D domains are also be treated by Winkler. So after this behavior, and especially taking into account that blow up is expected for 2D and 3D domains, it is more or less logical to consider a control in order, for example, to avoid this blow up. Or it can be also considered in order to drive the solution to constant states when times go to infinity. Or also in order to have a pattern formation, that is a non-constant steady solution, if we want to drive our solution to this behavior of the system. And other interesting question is where to put the control, because we have two equations, and in principle we can put the equation in one of them, in both, and in the equation or in the boundary conditions. So it is also, there's several possibilities, and we have centered especially in analyze this one, in analyze what we thought that it was the easiest one. So the easiest one were to put the control in the equation for V, because this equation is more regular. So in principle, it should be logical to obtain best results, at least to start to know what was exactly the behavior of the system once that the control is introduced inside. But of course, it is also logical to consider, or at least to ask about the possibility to put the control on the boundary conditions, or to put in the equation for U. As I said, this is the first result we obtain, and we consider the control in the equation for V. Why written in this bilinear form? And the first motivation was that if we put directly F, only F in this term, we must consider a positive control if we wanted to preserve the positivity of V. And for us, it wasn't so logical, because we wanted to treat with a non-regular control and to impose positivity for something which is not regular. It's not so logical. So we decide to put in this form, and we consider F without sign, and in principle we wanted only assume LP regularity for F, not regularity for the derivatives in time or in space, only for an LP regularity. And the system is exactly the same as before, but introducing this control term in the equation for V. Well, as I said before, this is a first problem, and is that the results that I explained before, for example, the proofs appearing in the article of Bellomo and collaborators do not apply in this case, because this term is not considered in the hypothesis. So we were forced to reanalyze again all the system and to see how the introduction of these terms interacts in the proofs that we did without this term. And the optimal control problem we considered was this one, was to try to minimize this functional that try to force what? Try to force U to a desirable state U, try to force V to a desirable state for the chemical substance V, and to do that with not very big f, or norm of f of the control. So we wanted to analyze that. And normally, if we want to prove existence of a solution for this optimal control problem, normally we will need to treat with strong solutions. So we were forced to study what was the regularity of the system once that the control was introduced in the chemotaxis model. So the main difficulties were, as I said before, that the classical results do not apply when introducing the control. It is difficult to prove uniqueness of a state once that the control is established. It is also difficult to have a priori estimates for the states U and V once that the control is considered. And normally there is not global in time regularity for the state. What we obtain in these cases were existence of global optimal solution, a first order necessary optimality system, and we obtain the existence and regularity for Lagrange multiplier associated to the system. But sometimes, especially in 3D domains, we were forced to impose a regularity criterion in order to have this the existence of such optimal solution. In the literature, before our works about control, we found some these references that were especially analyzed for the 1D domains. So these references refers to attractive chemotaxis, with the control introducing also, for example, here, the control is introducing in the chemical equation. In the paper of Pfister and McCarthy, the control was introduced in the equation for U, but the production term here in the equation for V was a little bit different, was this rational function. And also there were a work introducing the control on the boundary conditions, but in 1D, only in 1D. So, as I said before, we obtain existence of global optimal solution and first order optimality system for 2D chemorepulsion system when the production term is U to the power 1. In the 3D case, the same also for production term U. Guillén González, in collaboration with María and Villamizar, obtained a similar result for this one, for the chemorepulsion in 2D, but considering that the production term was U to the power P with P between 1 and 2. And now we are treating the 3D case for P between 1 and 2. And in the case of attraction of chemotaxis attractive, considering a logistic term and a 2D domain, we are able also to obtain this the existence of global optimal solution and first order optimality system. What are the main ingredients we use? So, as I said, this is the case of the chemorepulsion. So we have the equation for U and the equation for V, considering U to the power P or U to the power U, and the bilinear control in the equation for V. We need first to obtain the existence of solution. So we are able to obtain positivity of the unknowns, conservation, and global in time estimate for some mass. If we reproduce the same kind of tools used without the control, we use an energy equality, but now this new term appears due to the presence of the control. So we have to deal with and to try to bound. And we obtain similar results as before. But what is the explicit estimates that we obtain in this case? We treat with two kinds of spaces. the weak spaces, W, and the strong spaces, X. So normally we obtain regularity wake for U, for the living organism, and strong regularity for the chemical substance. So this both equation, wake and strong, will appear in next slides. In the 2D case, for the chemorepulsion model, we are able to obtain existence of a strong solution, a strong for U and a strong for V, assuming that F belongs to something a little bigger than L2 plus something. And we are able to obtain this continuous dependent estimate that says that if F belongs to this space, we are able to obtain a strong solution for the system. And the tools obtained is the Leray-Schauder theorem, writing the fixed point in a convenient form in order to preserve the positivity of the solution, which is very important in this biological system. And after that, we obtain bootstrapping argument in order to increase the regularity of the solution. And the functional, well, is the typical one. We obtain the approximation of U to the desired state U in L2 norm, the same for V, and the norm for F is L2 plus, something a little bit bigger than 2. But in the 3D case, we have a problem. We have to assume, of course, more regularity for F. In order to simplify, L4 is something bigger than L2 plus, something L2. But if we consider L4, we are able to obtain wake solution, wake for U and strong for V. But this is not enough in order to tackle the optimal control problem. So we need to increase the regularity of the solution. And there it is necessary, we don't know how to do that without imposing this additional hypothesis. We need to assume that U is a little more regular. If we assume that, we are able to prove that the solution is strong as in the 2D case. And we are able to reproduce a proof similar to the proof made in the 2D case. Of course, the method is similar. We also use Leray-Schauder theorem, but we need to regularize the system to obtain existence of the regularized problem, and after that to take the limit in order to recover the strong regularity for the primal problem. As in principle, we don't know if the solution is more regular. If we have this additional hypothesis, what we do is something more or less standard in optimal control, that is to assume that the functional we want to minimize is bounded. And if we impose that the approach of U to the desired state U is not in L2 norm, but in L20/7, which is exactly the regularity needed in order to have a strong regularity for our problem, if we know that this part is bounded, we have the additional hypothesis, and we can recover the strong regularity for the solution that make possible to tackle the 3D minimization problem associated to this functional. So this is the reason why the functional here is a little bit changed with respect to the 2D case. And if we have that, we are able to prove also the existence of the optimal solution. The optimal solution is based on the minimized sequences. So this is the existence of solution, but we want also to obtain first optimality conditions. And in order to prove that, what we use? We use several results, classical, because they are quite old, that makes that if we want to minimize this functional subject to GS. GS means that the solution satisfies the chemotaxis problem. We need to prove that the admissible set is non-empty. We define the Lagrangian associated to this functional. We define what it is called the Lagrange multiplier associated, and this needs the derivation of the functional and also the system of equation, the linearization of the system of equation for the chemotaxis problem. And the main tool is this result that says that the existence of Lagrange multipliers is associated to the existence of solution of this problem. And what is that? That means that we need to prove that the linearized problem associated to the chemotaxis has solution, has always solution. So this is what it is called a regular point. So if this system has a solution, we can deduce the existence of the Lagrange multipliers associated to the optimal control problem. I will visualize how we prove that, not in the chemorepulsion case, but in the attractive one. So imagine that now we are dealing with the attractive system, this attractive system with logistic source. And this is the equation for the chemical substance with the control. So in this case, we treat 2D domains, and we are able to prove only existence of weak solution, weak for U and strong for V. So this is the result, only assuming that F belongs to L plus, something a little big than 2. We are able to prove this estimate, and we state the same functional than in the 2D case, because here it is not necessary to assume any additional regularity hypothesis. And first of all, we prove the existence of solution by using, again, Leray-Chaudhary theorem. And after that, we need to see if the optimal control problem has a solution. The existence is through the minimizing sequences, and now the existence of Lagrange multiplier is associated to the existence of this problem. So this is the problem satisfied by the linearized problem associated to the chemotaxis system. So small u and small v are the solution of the chemotaxis system, the initial one, in this case, attractive. Capital U and capital V are the solution to the linearized problem associated to the chemotaxis system. So if we are able to prove that this problem has a solution, the previous result says that the existence of Lagrange multipliers is true. So this Lagrange multiplier satisfies this problem. So in some sense, we are saying that the Lagrange multipliers are the dual variable associated to the solutions of the linearized primal problem. After that, we are able to write in another form, and it is possible to prove that Lagrange multiplier satisfies this PDE problem that is a little bit more regular than the regularity deduced only as dual variable associated to the linearized solution. And finally, this is the regularity. The regularity is similar. Well, it's just the contrary. If the solution UV belongs to the weak and strong solution, the Lagrange multiplier satisfies just the opposite. And and recently there are some similar results even for 3D domains that has been improved by Guillén González and Correa Viana, just very recent. And these have been associated to an attractive problem, but considering a different term. Instead of considering production, it is also possible to consider something called consumption, because here the sign of this term is minus, so this decrease in some sense the chemical substance. So to finish, the conclusion in chemorepulsion are, well, we are dealing with bilinear control that forced to reproduce the system reset because the classical arguments doesn't work here. In 3D domains, it is necessary to assume regularity criterion in order to have existence and well-posedness of the optimal control problem. The existence of the global optimal solution normally is proved by minimizing sequences and also by convexity in some cases. And we have been able to prove the existence of Lagrange multipliers and also the regularity. So, and in some cases, we are able to prove that, assuming that the regularity is strong for the living organism and the chemical. But, for example, in the last one, in the attractive case, we only consider the case of wake solution for the living organism. It is similar, the results obtained also for the chemoattraction, in this case, only for 2D and logistic. And well, the regularity always, it is very difficult in some sense, because we have to deal with solutions that are not strong. This makes difficult to obtain the uniqueness. So we must be fine in the details in order to guarantee that all the steps we have made are true. And well, this is the reference use. And thank you very much for your attention.
Muchas gracias, María Ángeles. Any question for this very nice talk? Very, very complete and explained in detail. So, any question, comments, alguna pregunta, comentario? María Ángeles, I have just a small question. Have you guys tried to obtain similar results in the case of boundary controls? Like you say that some people has tried to do this in 1D, but have you guys tried to obtain something in the case of boundary controls as well for multi-D?
Yes, we are. You speak about boundary to put the control in the boundary. Yes,
the boundary, yes.
Trying to do that, especially we are trying to obtain, but by using numerical approximations.
I see, yeah, because
1D.
But
exactly.
you are trying 1D.
Yes, at the beginning we are trying 1D,
okay.
Because we are in principle it's attractive, and we have it is necessary first to design the good approximations, numerical approximation, but we are trying to deal with 3 different boundary conditions: Neumann, non-homogeneous Neumann, and also Robin conditions, and also something not exactly is to put in a bilinear control as the normal derivative is equal to f multiplied by v, something bilinear also in the boundary. Yes, we are. It is not a continuous reset, but we are trying to see the effect of the control in 1D, and especially seeing that in the numerical approximations. Is it a work in progress now?
Thank you very much. Any more question, comments?
I have one.
Yeah.
If I may. Okay. One of my questions is, you see, in your control, you are looking for some control, and then you do not have any constraint, no, in the control, right? Constraint in the sense that I mean, your control cannot be large as you want in order to control the system. So where is the difficulty to consider, since you are working with an optimal control problem, what is the difficulty to do your analysis with control in some constraint, some L2 ball, in some ball in L2, for instance?
I don't know if you say trying to put a special domain in order to control.
No. For instance, you have the control, which is in
Yes.
some space that you formulate your problem. Okay.
Mhm.
So you're looking for some control in order to attain some goal.
Mhm.
Okay. And the control you are search in the whole domain, right?
Okay.
And what happens if you restrict the space or the set where you are looking for the control? For instance, if you restrict your search for some ball, for instance.
Some ball, for example, inside the domain.
Yes,
In
inside the
principle,
space, inside the space where you are looking for the controls.
In principle, we consider that the control is not in the whole, could be not in the whole space, in the whole omega. It could be in a part, in a small part.
I'm not saying the spatial domain. I'm saying in the space of the space of function where you are looking for the controls. You understand me?
But you want to treat a more regular control or not?
Yes, you can consider, but you have some restriction that, for instance, if you looking for some control in L2 of small omega, and now you are looking for the control in the ball of L2 small omega. You understand me?
Yes, but we have
in the ball of the L2 space.
We don't know, but I don't know. No, we are only deal with the form of the domain has been not considered, especially. We have not.
Yeah, because this is a question related to the application, because you are some restriction, no? You cannot use the net thing or something.
Yes, of course.
You have some cost, so you have some limitation to apply the control, no?
Yes, in this case, it's more difficult. If you consider the whole space, it is easier. If you consider a part of the space, it's a little more difficult to treat. We have to impose some additional hypothesis, I think, in order to recover this result.
Okay. Thank you.
Okay.
Thank you.
There is one question in the chat. I will read. So, María Ángeles, would it make sense to study Pareto or Neste equilibrium for these chemotaxis models? This is a question by Orlando.
I think it could be interesting. We haven't tried, but of course, but I don't know the difficulty, because the problem of the chemotaxis system is the chemotaxis term, because it is not a parabolic system. So I think I haven't tried, but I think that this additional term breaks a little bit the structure, and it must be more difficult to treat than a standard parabolic system. We haven't tried, but of course, I think it is it should be interesting to treat. Of course.
Yeah. I think even, I don't know, that Mauricio maybe knows, but or Diego, even to study Pareto or Neste equilibrium with bilinear control, I don't know if this has been done. I'm not a specialist, but I don't think this has been studied by anyone. So that would be very interesting indeed.
The difficulty, maybe, at least in the controllability sense, is how to characterize the equilibrium. No, Mauricio?
Yeah.
because in the strategy that they use, they have some characterization which allow us to control the system. In the bilinear case, you have some nonlinear problem, so it may have some difficulty.
Yeah, I think it would be very difficult to study bilinear control through Neste or Pareto. Yeah, I think the problem is exactly to characterize what the control should satisfy. Yeah, I don't know.
Mm-hmm.
Yeah,
because when you compute the derivative, you also derivate the control, so you have the derivative of the product. So
and you have also in this case you need also regularity for gradient of f, for derivative of f.
yes.
It is possible. It is only that we wanted to consider the less regular control possible in order to reproduce, I don't know, for example, some medical outils that introduce, for example, to introduce a medicine in the system, is something that it is not continuous, something that it's very something punctual, something that it's not continuous in time and not continuous in space. If we impose more regularity for derivatives, also the existence of the solution for chemotaxis problem is easier, but we wanted to use the less regular one.
So, okay. So, any more questions, comments? I just check the chat. So there is not any more questions. So thank you very much, María Ángeles. It's very nice talk. And Diego, do you want to say something to finish the session?
Okay, thank you all the speakers and also the chairman of this section. So we thank you very much everyone to attend to the seminar. So that's all. So we close the session.